Hello everybody. We will be continuing with our lecture series on design of seismic resistant RCC residential building. Simultaneously, we also started another video lecture series on detailing of reinforced concrete elements. And in our last lecture of that video lecture series, we looked at the detailing criteria of reinforced concrete slabs based on IS 456 code and also SP 34. We will be continuing with our first video lecture series, that is lecture series on design of RCC residential building. And in this lecture series, in our previous lecture 11, we looked at some codal provisions regarding the design of slabs. Today we will perform the design of slabs. For that, I have here one Excel sheet in which the design is performed for one of our slabs, and that slab will be the critical slab. If you can remember our preliminary lecture, that was lecture 1 for this training series, in that lecture we discussed the preliminary design of beam, slab and column. And for the preliminary design of beam, we chose the beam with the longest span. And for the preliminary design of slab, we selected the slab adjacent to the critical beam, which had the longest shorter side. The critical slab was adjacent to the critical beam, and the second side of the slab, that is the shorter side, among the shorter side we chose the slab with the longest value of the shorter side, and we performed preliminary design for that critical slab. And if you can remember, we had two criteria, we followed two criteria for the design of the slab. One was the balance section criteria, and another criteria was based on the deflection criteria. We will be doing the same in this design video also. We will look at it a little bit more in detail. So let's start with that. If you do not remember, if you cannot remember what we have done in that first lecture, you can again revisit that lecture in our YouTube channel, Inquisitive Engineer. And before I start this video, I want to request all of you to subscribe to our YouTube channel and keep on liking our videos. And if there are any comments for further improvements, then you can comment under our video also. So let's start with the design of slab. If you remember this diagram here on the right hand side, this diagram I showed you during our previous videos also. This is the beam layout or the beam plan of our building that we designed in ETABS. And we can see here that our slab panel lying in the grid BC and 4-5, that is, this slab was our critical slab. In this critical slab, the larger dimension of this slab, the center to center dimension is 4.45 meter and the shorter dimension is 4.06 meter. So this was our critical slab. And for this critical slab, we will be performing the design of our slab. So let's see here. First, we have our center to center dimension 4.45 meter in the longer side and 4.06 meter in the shorter side. Remember that our slab are monolithically cast with the beams, and the beams are supporting the slab on all four sides. Our size of our beam, or the width of our beam, is 230 mm, that is 0.23 meter. This is the width of our slab, 0.23 meter. So what will be, let's look here, what will be the clear span in the shorter and longer direction. Since our center to center distance is, suppose let's look at first at the shorter side, 4.06 meter center to center span. Now we have to subtract from this dimension 4.06 meter half the width of beam on this side and half the width of beam on this side to get the value of clear span. So our formula will be, let's look here, 4.06 meter minus half means 0.23 by 2 on one side, and again minus 0.23 by 2 on the other side. You will get 3.83 meter. And similarly, in the longer span, 4.45 meter minus half the width of beam, 0.23 by 2 on one side, and again 0.23 by 2 on another side. You will get 4.22 meter. So we found the clear span. And grade of concrete will be grade of concrete will be 20 Newton per mm square. Sorry, this is, let me correct this. This is Newton per mm square. And grade of steel is 500 Newton per mm square. That is 500 grade steel and 20 grade concrete. Let's suppose that the unit weight of concrete is 25 kilonewton per meter cube and clear cover in our slab is 15 mm. So remember this. I would like to let's look here. If this is suppose our section of our beam or slab, whatever you may say, and suppose, okay, let me just erase this and let me draw the section of a beam. Suppose this is the section of a beam and we have reinforcement in the upper side, these three rebars, and reinforcement in the lower side, these three rebars, and then we have our stirrup here. So the distance between this lower face of the beam here to this stirrup, outside of this stirrup, suppose if this is the outside of our stirrup, then this is our clear cover. And what is the effective cover? Effective cover means you have to first find the centroid of the reinforcement in this tension side. Since we only have reinforcement in one line, the centroid will pass through the center of these bars. We suppose that the bars are all of equal diameter, so the centroid of these three tension reinforcement group lies or passes through the centroid of this bar. So the distance from this centroid or the center of this bar to the lower surface of this beam, this is the effective cover. This is the effective cover. So this is the clear cover and this is the effective cover. So our clear concrete cover for slab is 15 mm and bearings of slab, that is slab width, is 230 mm. So let's first provide an overall depth, or let's suppose the overall depth of our slab. Here we used one formula here. Sorry. We suppose that our overall depth of the slab is obtained by dividing this short span 3.83 meter by 30. That is 3830 mm by 30. We get almost to be 127.67 mm. Even in our preliminary design, we obtained the thickness of our slab to be somewhere 125 or 130 mm. So first let us suppose that the overall depth of our slab is 125 mm. And let us suppose that the bars in the short and in the long direction are 80 mm. So what will be the effective depth? If we go again here, this is our slab. Here we have bars in shorter direction. We saw in our previous lecture of this series that the shorter bars are always kept at the bottom and followed by longer side bars at the top, and those two bars are tied properly. So this bar at the bottom is shorter bar, and then we have longer direction bar at the top. So let us suppose that both these bars in the shorter and longer direction are 80 mm. So what will be our effective depth then? Our effective depth will be total depth 125 mm minus clear cover. minus 15 mm minus. Now for bars in the or for slab in the shorter direction, this reinforcement at the bottom will be our last layer of reinforcement, because this bottom reinforcement is our reinforcement in the shorter direction. So to find the effective cover for the slab in shorter direction, we have to take the dimension from centroid of this reinforcement layer, this bottom reinforcement layer. So in this bottom reinforcement, we also have supposed it to be 8 mm. Now we have to subtract total thickness of slab minus clear cover minus 8 by 2. And this will give us, suppose, let me just zoom here. If this is our concrete layer, bottom layer of concrete, and this is our slab, this is our rebar in the shorter direction, and this is our rebar in the longer direction, then you have to find the effective depth of this slab by subtracting from total depth first this clear cover up to this lower surface, and then from this middle of this bar this much. So this will be 8, whole diameter of bar 8 divided by 2. If you want to find the effective depth of the bar in the longer direction, then what you have to do, you have to find the distance. Since these are the bars in the longer direction, you have to find the distance from this concrete surface to the centroid of these bars. This will be our effective depth in the longer direction. So our effective depth will be 125 minus this whole diameter. First let us subtract clear cover 15 minus the diameter of shorter direction 8 minus 8 by 2. This will be our effective depth in the longer direction. So let's continue in our Excel sheet. We provided diameter of bars in short and long direction both 8 mm. So our effective depth, this is the effective depth in short direction, that we get to be 106 mm, and this is total depth 125 mm minus 15, which is our clear cover, minus 8 divided by 2. This 8 divided by 2, we get 106. So this is our design data. Now our loading on our slab will be dead load of the slab. We will calculate it, the unit weight of concrete 25 into our thickness of slab, that is total thickness 0.125. We get this equal to be almost 3.13. We suppose floor finishing load to be 1 kilonewton per meter square. Sorry. And the live load on our slab is 2 kilonewton per meter square, since it is our residential building, and this is a slab of our bedroom. If it were the slab of balcony or corridor or staircase, then we would have taken live load to be 3 kilonewton per meter square, but here our live load is 2 kilonewton per meter square. So add these three loads and you get the total service load on the slab is 6.13 kilonewton per meter square. You have to multiply it by load factor of 1.5 to get design load. You will get 9.19. 6.13 into 1.5 is 9.19. So after that, find the effective span. To find the effective span, you have clauses in IS code. You have clause 22.2 for effective span of beam and slab. You can go through your code and look through these codal provisions. In A, you have for simply supported beam or slab. In B, you have for continuous beam or slab. There is C for cantilever slab, and in D, there are for frames. So you can go through this clause 22.2 in IS 456 code. So how I found out effective span? I found out by adding to this clear span the effective depth of the slab. So for shorter direction 3.83 plus 0.106, you will get 3.94, and for longer direction 4.22 plus 0.106, and this is 4.33, and Ly by Lx ratio 4.33 by 3.94 is nearly equal to 1.1. So this acts as a two-way slab. Now if you can remember, we learned that we designed the slab based on the moment coefficients given in table 26 or table 27 of IS 456 code. So let's go to IS 456 code, and in table 26 we have bending moment coefficients for rectangular panels supported on 4 sides with provision for torsion at corners. We will be using this table 26. This table 26 has values of alpha x short span coefficients and alpha y long span coefficient for various types of panel and for various values of Ly by Lx. So if you see here, our panel is at the edge and we have one shorter edge discontinuous and one longer edge discontinuous, or you can say we have two adjacent edges discontinuous. So that moment that panel condition is given in number 4. Two adjacent edges discontinuous, and from this number 4 we know that Ly by Lx value our is 1.099, which is very nearly equal to 1.1. So take this coefficient. For negative moment at continuous edge, take 0.053, and for positive moment at midspan, take 0.040. This you get the value of alpha x for short span coefficient. And for long span coefficient, for this same condition, our long span coefficient is constant and it is not based on the value of Ly by Lx. That is, our long span coefficient are all same, is one value for all values of Ly by Lx, which is 0.047 and 0.035. So these four values, 0.053, 0.040, 0.047, these four values I am writing, or I am extracting it to my Excel sheet. So here it is 0.053, 0.040, 0.047 and 0.035. These alpha x and alpha y values, and I have created two columns here for 1.1 and 1.2. If our alpha x alpha y value is not equal to any particular value of Ly by Lx is given in this code 1.01, 1.2, but instead lies between any two values, then we have to perform interpolation. But since our value is nearly equal to 1, we can use these coefficients. We can use these coefficients for 1.1, which is the same 0.053 and 0.04 and 0.047 and 0.035. We do not need to use these values of coefficients for Ly by Lx equals to 1.2. So let's just forget this. Our alpha x value will be 0.053 for negative moments and negative moments at the top, and 0.04 for positive moments at the bottom. Similarly, our alpha y values will be the same 0.047 and 0.035. Now using these coefficients, find the bending moment per unit width. And you can remember our formula is Ax or alpha x w into Lx square for mx, and for my alpha y w into again Lx square. Remember this Lx square on both. So find the moments mx and my based on these coefficients. Suppose, for example, for this negative moment at top, mx will be 0.053 into w into Lx square. Lx we have here 3.94, w we have here 9.19, and alpha x from this column and alpha y from this column. Let me just erase here. So 0.053 into w into Lx square you get 7.54. 0.04 into w into Lx square you get 5.69. 0.047 into w into Lx square you get 6.69. 0.035 into w into Lx square you get 4.98. Lx value get from here, w value get from here 9.19. In this way, you can calculate the bending moment. Now, the main design criteria for our slab is the depth of the slab or the thickness of our slab. So our effective depth of slab can be determined based on two criteria as we discussed in our preliminary design lecture. One is the criteria of flexural strength or balance section criteria, and another is the criteria of deflection for the control of deflection. So let's see here, we calculate four values of bending moments here. We calculated four values of bending moment here, and the largest value is 7.54. This is kilonewton meter per meter. Since per meter, because we are designing for unit width of slab. So our largest value of moment is 7.54. So use this maximum bending moment 7.54 kilonewton meter per meter here, and we have this formula for bending moment here, 0.36 times FCK times 0.46 into, inside bracket we have 1 minus 0.42 into 0.46 into 1000 d square. This is the formula for our bending moment. And remember that this formula changes according to the grade of steel used. You can see here this 0.46 that we have used. This 0.46 value is for 500 grade concrete. You get this is 0.46. If you can remember your course on RCC design, we saw that the depth of our balance section will be 0.46D in case of 500 grade concrete, or sorry, 500 grade steel, and if we have used 415 grade steel, then this becomes 0.48D. So this formula changes according to the grade of steel that we have used. FCK is 20, 0.42 is it is a value in the formula itself, and 0.46, remember this comes from the grade of steel used. In this formula we have all values, and we only have to find the value of D. Equate this formula or equate this equation with 7.54 kilonewton meter per meter. I changed this into Newton millimeter per meter, and this will be 7.54 into 10 to the power 6. This is equal to this equation. From this, perform calculation, and we get the value of effective depth to be 53 millimeter. So from the maximum moment, we found the effective depth of the slab required. Now let us check for reinforcement using this value of effective depth for the positive bending moment along the short span. See here, we have positive bending moment along the short span 5.69. If you remember the previous video lecture on coral provisions, we saw that most of our moments in our two-way slabs are transmitted in the shorter direction from the middle of the slab. Hence, the moment in the shorter direction is always larger than that in the longer direction. So using this value of effective depth, we check for the tension reinforcement for positive bending moment along this short span. We have the bending moment 5.69. We have another equation here. Use the value of this bending moment divided by this whole formula, 0.87 Fy 1 minus 0.42 into 0.46 into D formula. Bending moment, use this, Fy 500, and D we got the value 53. You get our area of steel to be 308.5 millimeter square per meter. This is the value of reinforcement at the, since this is the tension reinforcement for positive bending moment, this value of reinforcement is for the middle strip of our slab. So area of reinforcement comes out to be 308.5 millimeter square per meter. You can calculate the diameter of bars and the number of bars required from this value also. So we acquired the value of effective depth 53 mm from the flexural strength consideration. Now let us use that effective depth and check for the criteria of deflection control. To do that, first let us find the actual span by effective depth ratio. This actual span 3.936 meter is our short direction span. So short direction span divided by the effective depth that we got 53, you get this ratio to be 74.08. And then determine the percentage of steel 100 AST by BD. This AST value you calculated here 308.5 millimeter square per meter. B will be unit width and depth will be 53 mm. You get 0.58. So if you can remember, again I am repeating this phrase, if you can remember, because we have already looked at it in our preliminary design lecture. In that lecture we discussed about the modification factor for tension reinforcement, which was given in figure 4 of IS 456 clause. There you had a graph for percentage of tension reinforcement in the x-axis and modification factor in the y-axis. So we have got our percentage of tension reinforcement is calculated here. We got the percentage of tension reinforcement to be 0.58, and then now we have to determine the modification factor. And to determine the modification factor, here are various graphs of FS. FS means the steel stress in service loads, and that FS is calculated as 0.58 into Fy. 0.58 into Fy. Here is another related also, 0.58 into Fy into area of cross section required divided by area of cross section provided. Since the required and provided is the same, this will just be 1. So our Fs will be 0.58 into Fy, and 0.58 into Fy we get to be 290 Newton per mm square. So if you can see here, this graph at the base at below is the graph for Fs equals to 290. So now select the point 0.58 percentage of steel in this x-axis. Draw a vertical line from this point to this graph of Fs, and from the point where it touches Fs, draw a horizontal line to your left. You get the value of modification factor. So our modification factor we get to be, this is 0.8, this is 1.2, so the middle value. Our line fortunately is at the exact middle of these two values, so our modification factor will be 1. So our modification factor we got to be 1 from this curve of figure 4. And another criteria that we already saw in our first lecture, the basic value of span by effective depth ratio. We have various values of basic value of span by effective depth ratios. You can see this in clause 23.2.1. We had values of 7 for cantilever. We have 20 for simply supported slabs and continuous for 26. Since our slab is discontinuous at two ends, it is neither simply supported, neither continuous at all four ends. So we take the average value of 20 plus 26, which is 23, to determine the value of basic value by effective depth ratio 23. So this 23 into 1, you have to divide, or you have to multiply this basic value by effective depth ratio into modification factor 23 into 1 to get the permitted value of span by effective depth ratio, which is 23 into 1 is 23. Now let's see here, we got our actual span to effective depth ratios 74, but our permitted value is only 23. That is, we got our actual ratio to be greater than permitted ratio. In that case, our deflection control criteria is not fulfilled, and hence we have to increase the effective depth of our slab. Hence effective depth of slab should be increased. And now let us try an effective depth of 105 mm. You may have to perform these iterations 1 time, 2 times, or 3 times before you get to the point where your basic value to effective depth ratio is within the permitted limit. So for our first trial, or let us say for our first trial, we take the effective value depth to be 105 mm. And now check for using this value of 105 mm. Tension reinforcement for short span is plus bending moment is given by, we have another formula here. Let's not do this. We have formula here 0.87 Fy AST D minus Fy into AST divided by FCK into 1000, which is equal to 5.69. Since 5.69 is the bending moment for our short span, let's go up. 5.69 you got to be for positive moments at bottom. That means tension reinforcement at the middle strip. So in this formula, now we have the value of D here, which is 105 mm, and you have to vary the value of FST and then determine such condition in which this maximum bending moment or max bending moment capacity of our slab section based on this formula is greater than the bending moment that is coming onto the slab due to the loads. We got our positive bending moment to be 5.69 kilonewton meter. Now we have to determine the bending moment capacity in such a way that the capacity calculated from this formula is always greater than this bending moment here. And how can we vary the capacity? Our only factor that is left to be varied is AST or steel reinforcement. So here I have a counter, some sort of a counter here. You insert the value of AST here until this capacity is greater than or equal to this bending moment. I have 125 here. Suppose what I'm getting using this 125 is that this capacity is less than this bending moment. See here, this bending moment value is 5693345 Newton millimeter and here 553. So this capacity is less than bending moment. So let me increase this AST to not being able to write here, so let's go to home. Let me increase this AST to 130 for now. It's okay. Look here, now this value here is greater than this moment that is coming onto our slab. So 130 will be our area of steel. Now again, using this area of steel, now again you have to check for the basic value of span to effective depth ratio. Now how do we do that? Let us see here. In this case, actual span is the same 3936. Now effective depth ratio is 105, which we assumed here 105. We get this to be 37.49, and our percentage of steel reinforcement is 100 into AST by BD. AST is 130 into BD. B is 1000 mm and D is 105 mm, which will get to be 0.124. Now using this value of reinforcement 0.124, again draw a vertical line first to this Fs is equal to 290 graph and then draw a horizontal line to get the modification factor. You get the modification factor to be 1.55 approximately. Multiply this 1.55 and 37 and this basic value 23, which is the same as above, to get the value of permitted value of span to effective depth ratio, which you get to be 35.69, 35.65. So our actual value is 37.49 and our permitted value is 35.65. So still this ratio is not within our permitting value. So again, our actual S by D value is greater than permitted S by D value. In this case, again you have to increase the effective depth of slab. Now let us see here, 125, we have already taken this 105 mm effective depth of slab, and using this value we get our total depth of the slab to be around 124 125 mm, which is equal to 5-inch slab. And that 5-inch slab means that is the normal depth of our slab that we use in residential buildings. So it does not do us good to increase the effective depth once again. So instead of increasing the effective depth, what we will do here, I am erasing this once again. We will increase the percentage of steel here, because you can see here, increasing the percentage of steel, what will happen here? Let's see. If I use 135, our actual span to effective depth ratio is, what is happening to our actual span to effective depth ratio? Sorry, not actually span to effective depth ratio. You see that our modification, this permitted value of span to effective depth ratio is it is influenced, this permitted value is influenced by our modification factor. So higher the modification factor, higher will be our permitted value. To get this higher value of modification factor, we see that we have to use lesser value of tension reinforcement. So what we will do here is, either you have to decrease the value of tension reinforcement here in this counter that we saw, or you have to increase the effective depth of slab. So you have to see if there is space to decrease the tension value of reinforcement. Our bending moment capacity here is, there is not much difference between capacity and this actual bending moment value here. It is 569 and 575, so we may not have space to decrease the value of steel reinforcement here. In that case, we again have to increase the value of effective depth. So I'm again going to this our first part, and instead of 105, I'm using 100 and let's use 110. So now it's okay. It's not, sorry, 110. Still, it is asking for the effective depth to increase. Let us say 112. Now it's okay. So you have to see that our permitted value of span to effective depth ratio is lesser than or equal to our actual, or our actual span to effective depth ratio is lesser than or equal to the permitted value. By increasing the effective depth to 112 mm, we got, let's say 111 mm, because our overall thickness 131 mm, it is not, let's say 111 mm. So our overall thickness of the slab will be now 130 mm. So our effective depth we got to be 111 mm. Now overall depth, you get effective depth plus half the diameter of the bar plus clear cover, you get 130 mm, because effective depth is 111 plus 8 by 2, that is 4, plus clear cover 15 mm, which you get 130 mm. So the minimum reinforcement in our slab should be 0.12 percentage of area of slab for high strength deformed bars. So we get this to be 156 mm square per meter. This would be our minimum thickness of, or the minimum reinforcement in our slab. So now we have found here the effective depth in the longer direction, which I already talked in the beginning part of this lecture, how to calculate the effective depth in the longer direction. For shorter direction, it will be 130 minus 15 minus 8 by 2, that is 4. You get this to be 111 mm. And for longer direction, 130 minus 15 minus 8 minus 4. And that you get to be 103 mm. So now we have determined the thickness of the slab. Let us find the reinforcement finally. Here there are two tables. First is the table for bending moment, and second is the table for reinforcement of steel. What formula we have linked here is that you have to change the amount of steel in short span and long span, and based on that amount of steel, a formula is used to calculate the moments here in long span and short span. And if using that area of reinforcement, our bending moments are larger than what we have acquired at the first, that is by using our formula for mx and my, using those bending moment coefficients alpha x and alpha y, what formula has been linked here is that if we get the value of moments greater than those actual values of moments coming onto them, then it's okay, and the value of the moments that is shown here is the value of those same moments that we have got previously. But if using this area of reinforcement, our moment capacity comes out to be lesser than those that we have got using this bending moment coefficients, then you get this increase still option here. Increase still option here. So let me just say once again what I have done here, or what this Excel sheet has done here, is that you have to determine, or you have to insert the value of reinforcement, and using that value of reinforcement, the formula here calculates the bending moment capacity of the slab section. And if that bending moment capacity is less than the moment that we got by using those bending moment coefficients alpha x and alpha y, then it says to increase the amount of steel. And if it is okay, then it says okay, and it just gives the value of that moment here. For example, here for negative moments at top, the Excel sheet is asking us to increase steel. So for top reinforcement here, let us increase. It's 195. Let us say it to be 200. Now it's okay. Now the negative moment at the top is 7.54, which is the value of bending moment coefficients that we got previously. And it means using this value of reinforcement 200 mm square at the top, the moment capacity will be greater than this 7.54, so it's okay. Similarly, you have to increase for top reinforcement in the long span also, since it is asking us to increase steel. So let's increase 180 by 185. It's still asking us to increase steel 190. Now it's okay. Now the moment capacity that we get using these values of 4 values of reinforcement will be greater than or equal to the actual value of moments that is coming onto our slab. And one thing, check for another thing also here. We got our minimum reinforcement in slab to be 156 mm square per meter. Also make sure that all these 4 values of reinforcement are larger than this 156 millimeter square per meter. So our design is complete. We have got the value of thickness of the slab, we have got the value of reinforcement at all sections. Now using this value of reinforcement, you can perform detailing of the slab also. We have already talked about detailing in our previous lecture, in which we started a new lecture series on detailing of reinforced concrete structures. And I started that series in the middle of this first series because I hoped that it would be useful. After learning the design of slab, it would be useful for you to perform the detailing by looking at that video. So finally, our diameter of bars 8 mm, our short span, then our spacing of reinforcement you can calculate yourself, because we have designed the reinforcement per meter. After, for example, if you have to use 170 mm square area of reinforcement per meter, then you can calculate the spacing. Since you already have the diameter of our bar, you can do that. And our codal provision is that for main reinforcement, the maximum spacing should be either 300 mm, or there are two conditions. First, you have to calculate 3 times the effective depth, and second is 300 mm. So from these two, whichever is the lesser one, then the spacing of our reinforcement should be less than the lesser value. For example, 3 times into effective depth, 3 times into 111, you get 333 mm and 300 mm. So the lesser value is 300 mm, and our spacing should also be less than 300 mm. So manage or calculate the spacing based on this criteria. So this brings us to the end of this lecture on design of slabs. We designed a two-way slab here. There may be some confusion because I have not done it step by step here, but rather explained in an Excel sheet. So if you want the Excel sheet, then comment with your email under this video, and I will be emailing you with the Excel sheet used in this design. And in our next lecture of this video series on design of seismic resistant RCC building, we will probably look at the design of a staircase. So this brings us to the end of this particular video today. We shall meet again soon. Thank you.